the temperature difference between the body as well as the surroundings. This is measured by using calorimeter. The black body means the one which absorbs all radiations. So when this black body absorbs radiation, what are the conditions over here? That is, it doesn't emit at a particular wavelength. What happens to the energy? Energy is also said to be maximum if the wavelength is maximum. Hello everyone, I'm Rinda, Faculty of Physics from Vidhyaashram Pre-University College, Mysuru, welcoming you all to session 4 of chapter 11, and the chapter name is Thermal Properties of Matter. So today in this class, let us discuss about the last topics of the same chapter, that is Thermal Properties of Matter, out of which today my concept will be thermal radiations. So what is meant by these thermal radiations? It is the heat which is emitted out of the body. Okay, so thermal radiation is the heat radiations which is coming out of the body is called as thermal radiations. Whenever the thermal radiation is incident, what happens? There is certain amount of radiations is absorbed by the substance, and then after absorption, certain radiations are radiated out. That is, it is emitted out. That is, it is reflected. It is absorbed, it is reflected, as well as it is transmitted also. So the radiations undergo reflection, transmission, as well as absorption conditions. So this reflection, transmission and absorption condition is given as reflectance, transmittance and absorptance. So sum of all these three is said to be unity. Okay, let us study about Newton's law of cooling. So I told you calorimetry in my previous class, that is in the session 3. So the device what we use in calorimetry is calorimeter, and calorimeter is the device which measures the heat from that of the surroundings, the temperature difference between the body as well as the surroundings. This is measured by using calorimeter. So in order to identify Newton's law of cooling, the same instrument will be used in practical ways, but here in this case we are studying the theoretical aspect, where we'll be studying the mathematical ways of the Newton's law of cooling. So here we have the rate of loss of heat by the body is directly proportional to the temperature difference between the body as well as its own surroundings. So provided the difference is said to be not very large, it is a minute difference what it has got. So what is the Newton's law of cooling states? So the Newton's law of cooling states that the rate of loss of heat by the body is directly proportional to the temperature difference between the body as well as its surroundings, and that can be given as, suppose if minus dq by dt, the change, that is the loss of heat, okay, the changes which is taking place in heat means the loss of heat. If d minus dq by dt, Q is nothing but the one which represents heat with respect to time, that is dt. So there is loss. Loss is represented by negative sign. So minus dq by dt means loss of heat with respect to time. So at what? That is which is directly proportional to temperature difference, that is from the actual temperature to the T naught, that is the temperature of the surroundings. So now on removing the proportionality constant, we have got minus dq by dt is equal to k into t minus t naught. So we have this equation. So having this equation, let us see now what is that dq. So dq is given as, we have dq is equal to C, that is the specific heat, m is the mass and dt is the temperature. When dq is equal to C, m and dt, we have got minus C m dt divided by dt, which is equal to k into t minus T naught. So this is the temperature difference and this is the equation. By interchanging the terms, we have dt by dt, which is equal to minus K divided by Cm, and we have T minus T naught. So this is the small letter K which we are considering. So we have got this term to be capital letter K. So it becomes dt divided by dt is equal to minus K T minus T naught. So now we have dt divided by T minus T naught is equal to, this term goes to the other side, K into dt. Now we will have to integrate these terms. On integrating, we have integral of dt divided by T minus T naught, which is equal to minus integral of K into dt. So this integration can be done as integral of dt divided by T minus T naught can be written as log of T minus T naught after the integration, which is equal to minus Kt plus C. So here we have got log T minus T naught is equal to minus Kt plus C after integrating. This equation gives you a straight line which gives the curve for Newton's law of cooling. So this is all about Newton's law of cooling. So we have, what is that Newton's law of cooling? It is the rate of loss of heat by a body which is directly proportional to the temperature difference between the body as well as its surrounding. This is all about Newton's cooling. Next we have Stefan's law. So what is meant by this Stefan's law? So Stefan's law is nothing but the total energy which is radiated per second per unit area. So there is a radiation which is coming out. So what is the Stefan's law calculations exactly? It is like the total amount of energy which is radiated per second from a per unit area. From a unit area of the surface of the black body which is directly proportional to fourth power of its absolute temperature. So this can be easily given as the energy. How do you give the energy symbolically? So it is E. E is directly proportional to absolute temperature. So fourth power of its absolute temperature. So you can give that the energy which is the amount of heat energy. What energy we are talking about in this chapter? It is all about the heat energy and nothing other than that. So heat energy is radiated per second per unit area, and it is directly proportional to fourth power of its temperature. What kind of a temperature? It is the absolute temperature we are talking about over here. So that is all about the Stefan's law. Having this concept, we can just give E is equal to, removing the proportionality constant, we have sigma T to the power of 4, where this is called as Stefan's constant. Stefan's proportionality. Stefan's proportionality constant. This is all about the Stefan's law, after which we'll be studying about the distribution of energy in the spectrum of a black body. So you all know the black body means the one which absorbs all radiations. So when this black body absorbs radiation, what are the conditions over here? That is, it doesn't emit. There is no emittance, there is no reflectance, there is only absorptance. So absorptance is equal to, the value is 1. So the complete radiations which is incident, the thermal radiation which is incident on this black body is said to be completely absorbed. So there is a intensity of radiations which is absorbed to its wavelength. There are different wavelengths for different radiations. So when this is a case, there is a distribution spectrum. What is given over here? Distribution of energy in the spectrum of the black body is understood by this diagram. That is like the distribution of energy among different wavelengths of thermal radiations of the black body was studied by two of the people, that is Lummer and Princein. So here the curve is in the figure represents the variation of intensity of the radiation with wavelength of different temperature. So the curve means here there are curves and this is the axis. Here the curves, whatever is represented, will be given under the two axes, that is here variation of intensity in y-axis and Wavelength is said to be calculated in your x-axis, which is given by lambda. So we have intensity as well as wavelength relation given by x as well as y-axis, on which we are going to study now. So let us get into the spectrum analysis. So we have got conclusions for the study of the energy distribution of the spectrum of the black body by Lummer as well as Springsteen. That is, here you can see the energy intensity of the radiations as well as the wavelength. So this is the energy level curves. So we have got T1, T2 and T3, the temperatures. So how do you explain this curve? It is all about at a given temperature, body emits continuous range of wavelengths. Okay, it is a continuous range of wavelengths which is being emitted certain every temperatures. That is all about the first point. And the second point is the energy at a definite wavelength increases with increase in temperature. So what happens to the energy? There is increase in energy when there is increase in temperature at every point of the wavelength. Then next, the energy distribution is said to be not uniform because it has got different sort of energies at different temperatures. Therefore, the distribution is said to be not uniform, as well as at a particular wavelength called as lambda m. Lambda m means maximum wavelength. At a particular wavelength, what happens to the energy? Energy is also said to be maximum if the wavelength is maximum. So that is all about the third point. And the fourth point is wavelength at which the maximum emission of energy takes place, it decreases with increase in temperature. So wavelength at which the maximum energy emission is going on, at that wavelength, the wavelength decreases when the temperature increases, but when the same temperature increases, the energy increases. So that is all about this conclusion studied by Lummer as well as Springsteen regarding the black body radiations. So after which, let us study about Wien's displacement. So what is this meant by Wien's displacement? Wien's displacement is nothing but it's a product of both the terms. Which are both the terms? That is, it is a product of maximum wavelength to the absolute temperature is always said to be a constant. So what is Wien's displacement? It is nothing but the product of maximum wavelength to the absolute temperature is said to be constant. That is what it is given here in this definition. So Wien's displacement law is nothing but product of wavelength at which maximum energy is emitted. Okay, so if the wavelength is maximum, energy is also maximum. So if the temperature increases, wavelength decreases. Here we are talking about wavelength, energy and absolute temperature. So when there is increase in wavelength, there is increase in energy as well as the absolute temperature. So here we have got maximum, it is a product of maximum wavelength to absolute temperature, which is said to be a constant. So that is all about the Wien's displacement. So having all these concepts, so generally we know what is meant by the greenhouse effect. So what exactly is greenhouse effect? So we know that the radiations, that is the solar radiations get into. So suppose if you are using these greenhouse gases in order to maintain plants. The plants are covered in a house called as greenhouse. So there is a radiation, that is a thermal radiation, which is incident on the glass of the greenhouse, which is absorbed by the plants which is present over there. And the gas which is released, that is the incident ray, it gets reflected back. So when there is reflection, that is absorptance, emittance as well as transmittance, these three things takes place. So these emittance radiations, the radiations which is emitted, it is acquired by the glass, that is, it is held by the glass and there is no further movement, it doesn't cross over the glass. The same heat is present over there. So what happens to the temperature when the heat is present and not released? The temperature resides in the same place as well as the temperature keeps on increasing because the thermal radiations which is emitted by the solar radiations, it is constant. There is no stopping of the thermal radiations. It is a continuous distribution of energy. So when that takes place, what happens to the energy which is emitted? It is stored in the greenhouse. So the temperature increases. So there is temperature increase because the thermal radiations which is emitted, that is the infrared rays which is emitted, which has a longer wavelength, and this doesn't cross the glass of the greenhouse. So if it doesn't cross, there is accumulation of this infrared radiations as well as the temperature rises. There is rise in temperature. The same effect goes with the Earth also. Consider Earth as a greenhouse here, and the plants are we, that is the living beings and living things which is present over here. So which is the thermal radiation? It is the solar radiations which is present, and it emits certain radiations to the Earth's atmosphere. So Earth's atmosphere acts as a greenhouse. So when the Earth acts as a greenhouse, the incident radiations on the atmosphere is absorbed by the Earth. So when there is emission, that is re-emittance of the infrared radiation and absorption by greenhouse gases in the atmosphere, what happens? The temperature increases because there is no releasing of the radiations which is incident on the Earth. There is accumulation, just accumulation process after the incident takes place. Incident radiation is incident on the Earth. There is just accumulation. So what happens to the gas which is present over here? That is the greenhouse gases. It absorbs the radiations and the same thing stays over here. As a result, there is rise in temperature. So this is called as global warming, and it is caused by greenhouse gases. So these greenhouse gases are purely responsible for the global warming. That is, complete globe gets warmed up. That is, the temperature rises, it increases because you can't even stop the incident radiations which is occurring on it. So that is all about the greenhouse effect which is taking place. If there is rise in greenhouse gases, then the temperature increase will be more and more, which will affect the biotic system which is present over here, that is in Earth. So greenhouse gas is a gas that absorbs and emits radiant energy with the thermal infrared range, which causes the greenhouse effect. So which are the gases which causes greenhouse effect? It can be H2O, carbon dioxide, methane, nitrous oxide, as well as ozone layer. So here we have got human activity since the beginning of the Industrial Revolution, because of which the global warming is much more. That is, the greenhouse effect is more and more day by day. So that's all about your session 4 of chapter 11. So here ends your topic, that is thermal properties of matter. So in today's class, we have studied regarding the thermal radiations and black body, how the black body acts for the incident radiations. We have studied about Stefan's law, Newton's cooling, as well as this WEIN'S displacement, after which we studied regarding the greenhouse gases. Let us all meet in the next class, next chapter and new session. That's all for today. Have a good day. Thank you.